Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in this lecture, that is Introduction to DFA, we are going to understand what is a deterministic finite automata. So let's see all the topics of this lecture. Our first topic is Introduction to DFA, and our second topic is Five-tuple representation of DFA. So let's get started with our very first topic, which is Introduction to Deterministic Finite Automata. But before understanding what is a DFA, let's first see the types of finite automata. In the previous lecture, I told you that finite automata is broadly classified into two types: finite automata without output and finite automata with output. Finite automata without output is further classified into DFA, NFA, and epsilon NFA. And in this lecture, we are going to understand what is a DFA. So let's get started. As I told you, the full form of DFA is Deterministic Finite Automata. DFA is a finite automata in which the transitions from one state to another state are deterministic. That is, for every current state, there is only one next state for a given input. Let's understand this point. DFA is a finite automata. So this thing I have already told you that DFA is a type of finite automata without output. In DFA, the transitions from one state to another state are deterministic, which means that in DFA, the transitions or movements from one state to another state are deterministic or unique. For example, if you are at the initial state Q0 and after reading an input symbol A, you reach the state Q1. Now this is called as a deterministic or a unique transition because we are getting only one next state for current state Q0 and an input symbol A. There is only one fixed path from Q0 on input symbol A. No confusion and no multiple paths. So this is a deterministic transition. But if I modify this diagram and add one more transition from Q0 to Q2 on input symbol A, now this is called a non-deterministic behavior because there are two next states for the initial state Q0 having the same input symbol A. So there are multiple paths and there is a confusion to select one path. These two transitions are non-deterministic transition because there is no one fixed path from the state Q0 on the input symbol A. But if I replace this input symbol A with any other input symbol, for example B, now this is totally fine and it is valid in a DFA because now these two are the separate unique transitions. This is a transition from Q0 to Q1 on the input symbol A, and this is a transition from Q0 to Q2 on input symbol B. So these are two next states, but for different input symbols. So this is allowed in DFA. So we can conclude that in DFA, for every current state, there is only one next state for a given input. That means for every current state, there is only one next state for a given input symbol. So I hope you have understood this point. Now, do you think it is a complete DFA? No, it is still not a complete DFA because in DFA, each state should have a transition for each input symbol. That means for every state in a DFA, there should be the transition for each input symbol in the alphabet. Now suppose our alphabet sigma equals A, B. That means there are two symbols, A and B. So there should be the transition for both the symbols A and B from every state in this DFA. If you closely look at this DFA, you will find that the state Q0 has both the transitions for input symbol A as well as for input symbol B. But the states Q1 and Q2 don't have any transition for input symbols A and B. That is why it is still not a complete DFA. In order to make this a complete DFA, we need to add transitions on state Q1 and state Q2 for input symbol A and B. So let's add transitions on state Q1. So it is a transition from state Q1 on input symbol A, and this is a transition from state Q1 on input symbol B. Now we will add transitions on state Q2, like this. So this is a transition from state Q2 on input symbol A, and this is a transition from state Q2 on input symbol B. Now we can call this a complete DFA. But it is to be noted that the transitions I have added in this DFA are just random transitions to make you understand the concept. But when we solve the problems of DFA, we have to make the transitions logically as per the problem. So I hope this point is now clear to you. Let's see the next point. Every transition must be triggered by a specific symbol from the alphabet. Hence, epsilon is not allowed as an input symbol. Now, what does that mean? It means every transition in a DFA must be triggered or caused by a specific symbol from the alphabet. And we know that there are only two symbols we have assumed in the alphabet, that are A and B. So this point means every transition should be caused by an input symbol from the alphabet. And in this DFA, we can see that for every transition, there is an input symbol. But if I remove this B from this transition, then this transition will be called as a null transition or an epsilon move, which is not allowed in DFA. And since this transition is now a null transition, this transition diagram is not called as a DFA because epsilon is not allowed as an input symbol. So I hope you have understood what is a deterministic finite automata, and you know how to check whether a given transition diagram is a DFA or not. So let me show a few more examples, and now you have to tell me whether that diagram will be a DFA or not. So here is the first diagram. Now you have to tell me, is it a DFA or not? Correct. It is not a DFA. Let's find out why. Because in this diagram, you can see this state Q0 has the transitions for both the input symbols A and B. But these two states don't have any transition for input symbol A and B. And I have just told you that in DFA, every state should have a transition for all the input symbols. That is why it is not a DFA. Now, this is the second diagram. And now tell me, is it a DFA or not? Again, correct. This is also not a DFA. Why? Because in this diagram, you can see this is a non-deterministic behavior. For the same input A from the state Q0, we are getting more than one next state. And I have told you that for every current state, there should be only one next state for a given input symbol. That is why this is also not an example of DFA. Let's take our third example. Tell me whether this is a DFA or not. This is also not a DFA. Let's find out why. Because in this case, you can see this transition is an epsilon transition or a null move. And I have told you that every transition in a DFA should be triggered by an input symbol. But here, there is no input symbol. That is why this transition diagram is not a DFA. Now let's take our last example, and you have to tell me whether this is a DFA or not. Yes, this is a valid DFA. Let's find out why. Because in this case, you can see every transition is a deterministic or unique transition. Also, every state has a transition for all the input symbols of the alphabet. And there is no epsilon transition in this DFA. That is why this is a perfectly valid DFA. So I hope you have understood what is a deterministic finite automata and how to check whether a given transition diagram is a DFA or not. In this way, we are done with our very first topic, Introduction to DFA. Now we are going to proceed with our second topic, that is the five-tuple representation of DFA. Now, while explaining grammars, I have already told you the meaning of the word tuple. Tuple is the ordered collection of elements. And here you can see DFA, which is represented using the uppercase letter M, is the ordered collection of 5 elements. And that is why DFA is called as a five-tuple. Now these 5 elements are Q, sigma, delta, Q naught and F. Let's understand these 5 elements one by one. The uppercase Q is the finite and non-empty set of states. So whatever the states you have in the DFA, that are Q0, Q1, Q2, Q3 and so on, if I create a set of all those states, that set is called as Q. Second is sigma, which is called as input alphabet. Input alphabet you already know. It is the finite and non-empty set of symbols. So whatever the symbols you use in the DFA, let's suppose A, B, C, 0, 1 and so on, if I create a set of all those symbols, that is what input alphabet is. Third is delta, which is called as transition function. Transition function is the collection of transition rules. And transition rules you already know. These are the rules which determine the next state on the basis of the current state and the input symbol. This is the equation of transition function, which we will understand in some time. Q0 is the initial state of the DFA. So the state from which the processing of an input string starts in DFA, that state is called as the initial state, which is represented by Q0. F is the set of final states. Now in DFA, there can be more than one final states also. So set of all the final states of the DFA is called as F. Then why Q0 is not a set of initial states? Because in DFA, there is exactly one initial state. There cannot be more than one initial state in a DFA. So I hope you have understood the meanings of all these elements. Now we will find out the values of all of these elements one by one with reference to the given DFA. So let's start finding the values of each and every element. Let's start with the uppercase letter Q, which is simply the set of states. In this DFA, you can see that there are only 3 states, Q0, Q1 and Q2. And the set of all these 3 states is called as Q. So Q is equals to Q0, Q1 and Q2. Next is sigma, which is the input alphabet, the set of symbols. You can clearly see in this diagram that there are only 2 symbols used, A and B. So sigma or the alphabet is the set of only A and B. Now let's find out the value of delta, that is the transition function. Transition function, as I have already told you, is the collection of transition rules. And a transition rule can be represented in the form of this equation. Transition function delta is Q cross sigma is giving us Q. This Q is the current state, this sigma is the input symbol, and this Q is the next state. For example, we have the current state Q0. On reading the input symbol A, the next state is Q1. So the current state is Q0, the input symbol is A, and the next state is Q1. So this is a way of representing a transition rule. And in this way, we can write all the transition rules for this diagram. In this diagram, there are total of 3 states and 2 input symbols. So the total number of transition rules will be 3 multiplied 2, equals 6. So there will be total of 6 transition rules. And the collection of all these transition rules is called as the transition function delta. Now, this cross represents the Cartesian product. And the Cartesian product is between the set of states Q and the set of symbols sigma. So this is the set of states and this is the set of symbols. Cartesian product means that every element of the set Q is to be operated with every element of the set sigma. That means Q0 is to be operated with both A and B, Q1 is to be operated with both A and B, and similarly, Q2 is also to be operated with A and B. And the Cartesian product is giving us the next state, which will also belong to the same set Q. Here you can see, on operating Q0 with A, we get Q1. On operating Q0 with B, we get Q2. And similarly, we can get all the transition rules. So I hope you have understood what is a transition function. Now let's move towards the fourth element, which is the initial state. In this diagram, the initial state of the DFA is Q0. So the value of Q0 will be Q0 itself. The fifth element is the set of final states. In this DFA, there is only one final state, which is Q2. So the set of final states F is equal to only Q2. So I hope you have understood all these elements perfectly. And in this way, we have completed our second topic, that is five-tuple representation of a DFA. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.